Welcome to the Ex Terra Podcast. The Ex Terra mission is to explore and discuss the business of space and its effect on the national and global economy, as well as life on Earth. How does what happens in space affect your life every day? That's what we're exploring on the Ex Terra website, as well as on this podcast. My guest is Adrian Nixon, Editor-in-Chief of Nixene Publishing. Adrian, thanks for joining me.
Welcome.
Let's talk first about your background a little bit. How did you go from chemist to publisher?
Yeah, it's a really good question. Right, I'm an industrial chemist. I've worn a white coat, worked in labs, invented things, and I climbed up through the company ladder. I got my degree through the Royal Society of Chemistry as well, by the way. So I've done it the proper way. But I got promoted, ran laboratories, and then you get so far in an organisation when the only thing you can do is either take out a contract on your boss or try and find some other way around. And I didn't have the mechanical knowledge to do the brakes on his car, so I decided to go the other way. And I did an MBA, master's degree in business. So I got science and business. That then took me up into market information management, where I was analysing companies, products, distilling them down to really clean information for decision makers. And I was really good at it. And then my company got taken over. I got offered a job in Switzerland, which I had a chat with my wife and we decided no. And I left and set my own business up, doing strategic planning, looking into the future for companies, doing workshops for board level people. Did that for probably about 15 years. And then gradually I'm getting a bit bored of it because, you get picked up, put down in one part of the world. An office in America looks very similar to one in the UK as in Europe and Asia. It doesn't really matter too much. And I started to get more interested in science again. I started to look more doing futurology sort of things. So I had a lot of material it was all the stuff on the cutting room floor, if you like. And nobody was interested in it because it was too long term. So I gathered this all together and started to present it at business schools and got quite a good warm reception for it. And one of the things that kept coming out time and time again was this stuff called graphene. As a chemist, I was interested in it. And then gradually I got more and more interested until the point was I thought, you know what, I fancy devoting my life to this. So I started writing about graphene for an investment blog for the financial community. And then from that, then came some consultancy work to do some private consultancy for some businesses, briefing them about graphene. And from that then came, this would make quite a good journal in its own right. And we've almost started a publishing company by accident. So we've sort of been market led. So that's how I've come from being a chemist through futurology, through science, getting interested in graphene, specializing it, and using all those skills in the science and distilling information, presenting it very clearly for customers. And now, the journal's doing really well and taking off to the point where you've heard about us and invited us on. So thanks for the invitation.
So why graphene? What's special about it?
It's really compelling because at one level, it's the simplest thing you can imagine. So it's the stuff inside pencils. So will your viewers and listeners know much about how graphene was discovered? Should I go there?
You can give us a little background on how that came to be. So
graphene is part of a material called graphite. It's just carbon, that's all. So you're all familiar with diamonds, and I like these molecular models. So I'm holding a molecular model of diamond, and you can see carbon atoms linked together in sort of 3 dimensions, a bit like a 3-legged stool, with a carbon atom at each foot, and then one sticking up in the middle. Hopefully the listeners will get that. That's a 3-dimensional form of carbon. Now, graphene is the same thing. It occurs in graphite. And now what I'm holding up is a model with 3 layers of what look like chicken wire made of hexagons, and the carbon atom, 6 carbon atoms per hexagon. And this material is same material as diamond. So graphite, the stuff in your pencils, is exactly the same chemically, except now these layers are held together by very weak bonds and they slide over one another. So when you draw a line on a pencil line on a piece of paper, you're shearing off these lines. Imagine having a deck of cards and smearing them out across the sheet.
Okay.
That is what's going on. Now, graphene is just one of those layers. So it is, and now I'm holding up another model. If you're listening, you really want to see the video. Then what I'm showing you here is a molecular chicken wire of graphene, and that's a larger model of a piece of graphene. Now, that is essentially what graphene is. It's just one atom thin layer that looks like chicken wire of graphene, of carbon. And when you're drawing a line on a pencil line on a piece of paper, you can all try this at home. If you lift the pencil towards the end of the trace, somewhere along that line, you will have made a piece of graphene. That tells you two things. One, graphene is incredibly simple to make and understand. And two, what the heck do you do with it when you've got it? Because it's just a pencil trace. So you've got to make it in industrial quantities for it to be useful. And that's where it starts getting more complicated. And we can go right into the science, but we've only got a certain amount of time here. Does that give you a rough idea about what graphene is, and you're beginning to pick up my enthusiasm for it?
Absolutely. So then what does make that such a versatile material?
That is a really smart question. So graphene was thought to be impossible to isolate because it's a two-dimensional material. It's one atom thin, and it could be quite large on the XY scale, so as a sheet. So before 2004, it was thought impossible for graphene to even exist. And two professors of physics at Manchester University were playing around with pieces of high-quality graphite, so a large crystal of graphite, and they put some sticky tape on the graphite and then peeled it off. And then the sticky tape that they got left, they put another piece of sticky tape on, peeled that off. And can you imagine you've got a deck of playing cards and you're putting sticky tape on and peeling it off? Eventually, and this takes 17 times of doing this, eventually you'll end up with just one layer of graphene left. And they first of all proved they could isolate it. So they proved everybody wrong. Then they started to look at what the properties were. This is where it gets interesting. They found that graphene is 200 times stronger than steel. Highest melting point of any material ever known in a vacuum, somewhere between 5,000 and 6,000 degrees. It's so high, they're still sort of trying to bottom that out, but this stuff could sit on the surface of the sun and still be there. It's non-toxic, it's not going to kill you. As far as anybody's found so far, and I look at the evidence a lot, there's no warning signs coming out yet, although don't breathe in the dust, it's just sensible. It conducts electricity better than copper. It's one of the world's best conductors of heat. It's transparent, it's flexible. It has all these superlative properties in one material. If graphene was a person, it would be a superhero.
Let's talk about the journal just a little bit and tell us about some of the products that you offer through the Nixene Journal.
Well, the Nixene Journal, do you remember I told you that I'm very good at taking complicated information and then presenting it easily for people to understand in plain English? So what I do is read as many of the academic papers that are coming out each month, and I look across all the commercial activity, the business activity that's taking place. I break that down into plain English and summarize everything on one page. So for viewers, for listeners, I'm holding up a copy of the journal. This is a paper copy. Most of our copies now are PDFs because electronic form is searchable. And what we do is, this particular one is for an organization for the geek. This is where I work in Manchester, the Graphene Engineering Innovation Centre. That's a $100 million building. And we get to work in it. It's great. And we did this for the opening of the Geek, so we were commissioned to write this. Here's an example of what one of the pages looks like. So this is a piece of research which shows you can make a patch out of graphene. Do you remember I said it was electrically conductive? These people here, they've made a sticky patch that contains a sensor made of graphene, and it can also talk to a mobile phone via near-field communications. And it analyzes body fluids that are coming up through the hair follicles, and it can tell you what your blood glucose levels are without an injection. Cool, isn't it?
Yeah.
Yeah, that's just one thing. So you can see here on the page, we got a picture here, I do all the graphics, explain what's going on, take apart all the impenetrable language from the researchers, but then we do something else as well. Each page has, at the bottom, there's a kicker box which says, so what? Relevance. So in couple of sentences, why this is important and why a decision maker needs to pay attention. Then you can go back to the detail. Then you can go to the references and see where we got our information from, so you can check what we're doing. But then the other thing is we've got these keywords that we put down the side on each page. So we've got a keyword for markets, the application, and the product type, and we standardize those. And over 5 years that we've been doing this, we've built up a whole list of information. So we can now start to do trends analysis on where the whole industry is going.
So go ahead, no, please.
No. Well, basically, we just take apart technical activity, scientific activity, commercial activity, turn it into plain English, one issue per page. So a decision maker can go straight to the stuff they're interested in, get the so what, and they can also see the context as well, how it fits in with everything else.
So then how is the journal different from sites that offer news? That's
another smart question. So there are sites out there, plenty of them. You can find that some specialize in graphene, others don't. Graphene is just an add-on, but other sites will say provide graphene news. So they take the PR from companies and repeat it, and that's it. What we do is we lift the lid on that and then explain what's going on to listeners to say, this is why it's important, this is what's going on, these are the good things, these are the bad things, or these are the things you need to watch out for. And so there's an element of analysis there as well that we're taking apart, lifting the hood, if you like. Then there are other organizations out there that are member organizations, but they have an interest towards their members. We, in the journal, we just survive on subscriptions. So, and with some very big companies too. So we don't take advertising, and we're completely independent, and we might occasionally upset people, but I'd rather do that than promote or repeat something which is false.
Isn't it something though of a niche market? I mean, so many people, until I got involved in this and also working with Stellar Modal, as I know you do as well, we'll get to that in a little bit, but I'd never heard of graphene.
Yeah.
Isn't it something of a niche market? And how do you then let people know that here's an independent journal that will tell you basically everything you need to know about graphene?
Yeah, another really smart question. You're quite good at this. Yes, it is a niche market, and there's a certain amount of educating customers that needs to be done. One, that graphene exists, and two, that it can do what it it can be transformative, and there are different types of graphene that perhaps we can come back to a little bit later. But this stuff is going to transform our world. It will be the material of a new industrial revolution, and people are just catching up with this. So, for example, some of the things that we're doing, already we've got people coming to us. So you'll know that NASA knocked on our door and asked us to actually brief them on what was going on in graphene. Graphene is not just one material, by the way. There's a whole landscape of what are called 2D materials. There's probably another 2,000 of these types of materials that are being explored at the moment. And they can be stacked and layered up in different combinations. So they're able to do all sorts of amazing things. And people don't realize this yet. We were also asked to create a briefing report for the Foundation for the Future that you may be aware of. This is a political action committee, and we were commissioned to create a briefing report for senators and members of the House of Representatives and policymakers in the US government, and telling them what graphene is, how it works, why it's important, and why they should pay attention, because there's a lot going on in the US, but graphene isn't stitched together yet at a national level. And boy, as this stuff starts to roll out and people start to realize what it can do, people are going to be clamoring for it. We're right at the beginning of this advanced technology.
We're talking with Adrian Nixon, Editor-in-Chief of Nixene Publishing, which focuses on the uses of graphene in a variety of areas, including space. And we'll get to that in just a moment. First, though, take a moment right now to click subscribe or follow to be sure you don't miss any of the podcasts, or if you're watching on YouTube, any of the videos from Ex Terra, the Journal of Space Commerce. Adrian, let's talk a little bit more about graphene and its applications in the commercial space industry. What have you been seeing so far?
There's an increasing amount of activity. I'll just talk about, first of all, I need to say the two types of graphene. So there are graphene powders. This is a graphene powder in dispersion in water. I can tell you that because I made that. Again, I'm a chemist, so I happen to play with this. Graphene can be made as powders, black powder, but it can also be made as sheets of graphene on a larger scale. Now, you'll have to take my word for it. This was made by a Californian company called Groltex. And And they're one of the companies in the world that makes graphene at a large scale. So what you're looking at here is a sheet of copper foil with a 1 atom thin layer of graphene covering the surface. So there's 2 different types of graphene to start off with. Most of the action at the moment is on powders. These are used as additives. So applications in space are just starting to come out. If you take this powder and put it into, let's say, carbon fiber composite, then you put it into the epoxy resin, it will increase the impact resistance and make the carbon fiber composite much stronger. It will also allow you to make, it'll improve the cryogenic performance, so you could make things like liquid oxygen tanks and things like that out of it, which you haven't been able to in the past because composite materials tend not to perform that well. There's a rocket, do you call them launch vehicles? Because I'm new to the space community. I'm a chemist.
Either way, that's fine.
Yeah, rocket launch vehicle. The body of the rocket at the moment is made from high quality aluminium, steel. I think Elon Musk uses steel for his rockets, doesn't he?
On Starship, he is, yes.
Yeah. The problem is steel's easy to manufacture, but the problem is it weighs quite a bit. Maybe we'll talk about rockets and how much stuff they got to throw out one way to go another way later. But carbon fiber composites haven't been used in the space industry much because variety of reasons. New technology, there's concerns about them standing up to the stresses and strains, but they are lightweight and very strong. You add graphene in, you can make a carbon fiber composite 30% stronger. And there's a launch company in the UK called Orbex, who are going to be launching from a new base that's being built in the UK. They've made the body of the launch vehicle from carbon fiber composite enhanced with graphene. So there's that. Other uses for it, you can make a graphene foam. Do you remember I said graphene has a very high melting point? So if you use the foam as a structure to hold the propellant inside the boosters, what Purdue University have just found last year was that the foam supports the propellant and allows the propellant to burn more evenly and faster, but the foam doesn't get destroyed. So you can launch rockets more efficiently and improve the power of the propellant. And then there's all sorts of other things. NASA are looking at going way into the future, building structures on the moon and Mars with regolith. This is the soil that you find there. Right. And the problem is that if you want to make structures out of there, you've got to take all the materials with you to get to your destination. So the idea is if you can use more of what you find locally and what you've taken with you, it's going to be an easier build. And what they found is that they can make things like polylactic acid from urine from the astronauts and use that to make like a plastic that will hold regoliths together. The only problem is it gets destroyed by UV light. So put graphene in, it helps enhance the UV protection and makes the polymer stronger. So you can use it to print houses on the moon and Mars. So it's already being thought of in those areas. I could probably go on for another week about all the applications. That's probably good for starting.
And we'll talk about a few more of those future applications in a moment. But let's talk first about nanoplate products. What is that and how is that used? Okay.
All nanoplate means is very tiny flat things. So you remember the graphene model, this chicken wire that I'm holding up. It's at the small scale, it's just one of those cards in the deck of playing cards I talked about, that's all. And it's called a nanoplate because it's on the scale of nanometers rather than micrometers or meters. So typically in some of these, you're probably looking at maybe 500 nanometers for a nanoplate. And it would look like a black powder, very, very fine black powder. Because it's so small, it can get dispersed and work its way into all the crevices and cracks between polymers and do its job really efficiently. And that's why these black powders are beginning to transform products like polymers, cement, and things like that by just being added. So that's what nanoplate means, just really small bits.
How do you convince people that this is, I'm reminded of an old W.C. Fields movie where he was selling basically snake oil and it cures hoarseness. It does everything. How do you convince people that graphene is the kind of product that you say it is, that it will do all of these wonderful things without having things to actually show them and say, well, here it is?
Really good question again. It's compounded by the fact that we've already had a bit of the snake oil stuff going on. A friend of mine describes the fact that the cowboys always get to markets first because they've got faster horses. And there have been a lot of people who've gone into the graphene world with the intention of ripping people off. In the early days, graphene products, graphene-like powders, they were added to polymers and things, and they just made it worse. It didn't work. And lots of people conned other people out of money, but also in good faith as well. The investors piled in. Graphene got a bad name, like a lot of new technologies. Overinflated expectations caused a hype. And we're still seeing some of that now we've got to overcome. So there has been sort of snake oil selling in the past. However, one of the best ways of getting around it is to prove that this stuff works. One example I can give you straight away is that you'll start hearing about in the States. It's just being applied in the UK over these last few months, is graphene in concrete. So if you take this black powder and you add 0.01% of this powder into concrete, that's almost nothing, it makes concrete 30% stronger. Staggering. When you think concrete accounts for, or cement production that goes into concrete accounts for about 8% of global CO2, and with COP26 on at the moment, and this is a live issue, so a lot of carbon being produced to make concrete. You can actually, by using 30% less concrete, then you're immediately reducing the carbon that's emitted into the atmosphere with no changes to our lifestyle whatsoever. We reckon that you could probably take 2% of global CO2 tomorrow if you use graphene in all the concrete around the world. Now, obviously, you don't dive into it immediately. You want to prove that it works. There are companies in the UK now laying graphene. I've stood on graphene enhanced cement. It's been done already. It's been laid on about a $20 million residential estate. They laid a floor raft. It was so strong, they didn't need to put in the wire cages, the reinforcement. And then they found another benefit. It's set faster than normal concrete. So normal concrete takes 28 days to achieve full strength. They achieve full strength in 12 hours. And you think what that does to construction timelines. Right. I saw a pour at what's called the Mayfield Centre in Manchester. This is a mezzanine floor that's just been poured. The finishers for the concrete were able to start work on the graphene enhanced concrete while the guys at the other end of the rink were still laying the wet stuff. It was set that fast. Staggering.
Let's look into the future a little bit and find out how you anticipate graphene is going to be able to be used in commercial space going forward. And I know there are many applications that have been talked about, like water purification, radiation protection, and then there's the space elevator. So let's get into some of those.
Okay, radiation protection very quickly. Graphene is very good at as an EMI shield, so it protects you against the wavy stuff. It doesn't protect you against little bullets. So your readers will be aware of this, that you have 3 types of radiation. It's less good at protecting against alpha and beta radiation, which isn't a problem on Earth, but when you don't have any air to stop stuff, then you really want something more substantial. But graphene can play a role there. It'll block out the electromagnetic parts, so gamma rays, X-rays. It's very good at that. So you can use that for shielding. And then for water purification, you can use the powders to make membranes. But MIT are also working on a process at the moment with this CVD graphene, the large area sheets, single layer. They're already making membranes with monolayer graphene on the surface already. So you can expect graphene membranes to start coming in for water separation, purify polluted water to make it drinkable. Also things like hydrogen economy. When you try and store hydrogen in tanks, it leaks out, even metal tanks, and it makes them brittle. Coat them in graphene, 2 layers of graphene will be impermeable to hydrogen. But there's another big thing going on. I mean, you can just imagine the impact of graphene on space. This monolayer graphene, this large area graphene, if you can make this sheet large scale in what's called a repeating pattern, a single molecule that's not just nanometers size, but meters, kilometers, hundreds of kilometers long, then that's called single crystal graphene. It's a single molecule. That's getting possible now. That can already be made by continuous manufacturing processes in small quantities, up to around about 500 mil at the moment. But bear in mind, that's a single molecule at 500 millimeters. That's massive, half a meter. Mm-hmm. So this is showing us that the way the manufacturing process is evolving, we'll be able to make large-scale sheets in incredibly long lengths. That now begins to open up the possibility for a piece of technology that's been on the sidelines of space for a long time, called the space elevator. Quite a lot of your readers will be aware of that. Do I need to explain how the space elevator works?
Let's go ahead and just give them a brief overview, sure.
Very brief. Okay, Tom. Right. So launch a geostationary satellite. So it's always above the same point in Earth. So if you stood beneath it, you would look straight up and see the satellite if you could, and it would always be above you. Then you take a cable and drop a cable from that satellite all the way down to the ground, anchor it at the ground, and then you can climb up like Jack and the Beanstalk and be in space. It sounds childish, but actually NASA invented this. One of the co-inventors.
It's been around for a long time. People have been talking about a space elevator.
Yeah, and at the turn of the century, gosh, that sounds a long time ago now, doesn't it? About 20 years, but the turn of the 2000s, NASA said, look, let's have a look at the space elevator. Is it really feasible with today's technology? And they commissioned a guy called Dr. Bradley Edwards, gave him a chunk of money and said, just go away, tell us, can this be done? He reported in 2003 that everything was doable with today's technology. So we can launch stuff up to build the station up there. We can build all the stuff on the ground. Everything in between, the elevator technology exists. That's all doable. Today's oil and gas technology will handle most of it, and combined with aerospace technology. The only thing that was holding it up was the material you make the tether out of, the piece of material that connects the satellite with the ground. There was no material strong enough to do the job. Even Kevlar and things like that would just break apart under their own weight. So the project was effectively stalled. And then somebody said, oh, well, there's carbon nanotubes. They're a bit like graphene, if you can imagine that chicken wire, but just rolled into a tube. But nobody's ever been able to make them long enough to do the job. So in 2003, it sort of fizzled out. Then in 2004, graphene was isolated. And then 2010, the Nobel Prize was won for the discovery, and everybody starts to get interested. And I start to get interested in this and find that I start publishing statistics about how strong graphene is, how light it is. And all of a sudden, the space elevator community found me and said, do you realize what this material can do? I went, no. And I hadn't heard of the space elevator. And then we started to have a conversation, just going from the science. I ended up talking with rocket scientists saying, well, is this material strong enough? What's the trajectory for the manufacturing? They were really hard guys to convince, but in the end, we ended up sort of really being quite robust with one another, but realizing, do you know what? This actually is doable in our lifetimes. And they got so excited that, well, they invited me onto the board of the International Space Elevator Consortium, and I'm now their tether specialist. So we can see that the tether material, which connects the space elevator to the ground, will be made up not of just one layer, but it would be a flat ribbon, probably somewhere between 0.5 meter and 300 mil wide, a foot and maybe 1.5 feet. And that is strong enough. If it's made of 12,000 layers of graphene, all sandwiched up on top of one another, that's easily strong enough to take a 20-ton crawler that would then clamp onto it and propel itself up from the surface of the ocean right up, and the next stop is space. And it would do that safely, and it would carry larger quantities than rockets are capable of doing, and it would do that with low carbon emissions.
I was going to say 20 tons is the amount of energy it would take to launch 20 tons into space is astronomical.
Yeah, because the way rockets work, as you know, because you hang around with rocket scientists and you're quite a bit one yourself, but you have to throw a lot of material out one way to go the other way. And that's roughly what a rocket is. It's is it Newton's first law of motion, something like that? And the net effect is that there's something like 0.5% of the mass on the launch pad will only reach the surface of the moon. So you've got to throw huge amounts of stuff out one way to go another way. And there's an awful lot of that can be handled at the moment. But if you think about it, if you want to try and achieve the targets that Mr. Musk wants to do, Mr. Bezos wants to do, if you actually work back, say you want 1 million tons to Mars, that is a huge amount of rockets. And you've got to question, is the technology actually capable of delivering that amount of stuff to space?
But if they send it up on an elevator to a space station, and then it doesn't take nearly as much energy to push it onto the moon or Mars.
Yeah, exactly. And what the guys I'm working with say is the first thing you do once you've built the first space elevator is you start to build others. And then you've got massively parallel tracks going up into space. And these things have a very small footprint. So, you wouldn't notice them from probably about a mile away. It'd be very difficult to see because we're not talking about substantial quantities of material.
We're going to run long, and that's just fine because conversation is fascinating. What has to happen, Adrian, before some of these things can become a reality?
Yeah, that's a good point. Right. A lot of people have got to be convinced. Arthur C. Clarke, the famous science fiction writer, wrote about the space elevator, and somebody asked him, how long will it take to build a space elevator? He said probably 50 years after people stop laughing. And there's a certain amount of truth in that. The technology has been dismissed quite a bit. People think it's science fiction. Trust me, this is more reality than most people appreciate, because the material science that I am living day by day and watching is accelerating faster than anybody realizes. So there's a certain amount of doing things like this, I suppose, just talking to people and saying, look, pay attention to this. It's not stupid. It's solid science. It's not there yet, but boy, is this stuff advancing rapidly. The second thing is keeping an eye on manufacturing technology and making sure that the graphene manufacturers have in mind ultimate destination for making very, very long lengths, very, very high quality, very, very consistently, very, very fast. When we first started out looking at graphene, it took, the speeds were in microns per minute. And that you can just imagine pieces of material just sort of growing in the lab like that. I monitor these things now. Just a few months ago, we've discovered that there is a roll-to-roll process for making graphene. So you start with one roll, reeling it up onto another, 400 mil wide, so just over a foot wide. And this can make graphene at 2 meters a minute already. So you can see that, and that. So going from microns a minute to meters per minute has taken place in less than 10 years, and the costs are coming down already. You project that forward, I reckon that a space elevator tether is doable in our lifetimes. And I've got grey hair.
So do I. Adrian, you're on the advisory board for Stellar Modal. How did you get involved with that organization?
Yes, Stellar Modal is the Space Transportation Association. So they're stitching together a lot of activity around getting things from the surface of the Earth up out into space and vice versa. And there are a bunch of really good guys. I know the president, and he's a good guy who I trust. He also works very closely with my colleague in the US, Debbie Nelson, who you know. And Debbie, as you know, is space mad. And Debbie sort of prompted me to carry on the conversation with John Weathersby, who runs Stellar Modal. We get on well with one another. We trust one another. John used to be the head of the National Graphene Association in America. And I was an advisory board member of that. And because we know one another, we trust one another, it was a natural fit for me to say, well, John invited me onto the advisory board. It was quite an honor for me to say yes. I don't say yes to everything. So guys out there, if you're listening, don't invite me onto anything else. I don't have the bandwidth. This about it in a minute.
One thing more, and this is a question we ask all of our guests, but look beyond graphene into your crystal ball and tell us what you see in the commercial space industry in the next 10 to 15 years.
10 to 15 years beyond graphene. I would say you're going to look at materials. I'll look at it from a materials perspective. So as well as graphene, there are other 2D materials. There's something called hexagonal boron nitride, something called white graphene. It turns out that this is a white powder or sheets of white material that it conducts heat even better than graphene. So I think this stuff will be used for heat shield applications. I'm already talking to somebody who is designing the next generation of space station modules. So he's working with the people that built the Burj Khalifa, you know, the tallest building in the world. Mm-hmm. And we've got a video that is on our YouTube channel as well, and you'll see it on LinkedIn if anybody's interested. But these modules are built from carbon fiber composites and also glass fiber composites, other types of composites too. So we could start to see new materials coming into the space arena. Also, because weight is really important in space applications, humble things like you can make graphene metal composites. So if you put graphene into metal wires, Pacific Northwest National Laboratory, PNNL, just on this, you can increase the electrical conductivity of copper by about 5%, which means you can lightweight with lighter weight copper wires because they've got this graphene in them. So you'll find that there'll be all sorts of new materials coming out. But also, can you imagine when they start making things like these 2D materials and they start being layered up, you'll have something that's as thin as, we call it cling film. I think you call it saran wrap in the States. Plastic film for wrapping up food in. Something as thin as that, it'll stop a bullet. And can you imagine what that would do for lightweighting, for construction on Earth, in space, automotive everywhere? Also, you'll find there'll be all sorts of amazing advances which don't have anything to do or apparently don't have anything to do with these new materials. But for instance, now if you buy a Ford car, they are quieter, more refined. The reason is that there are 5 million cars on the road already with graphene in them, enhanced by Ford. And very few people know about that. And it does something surprising. It deadens the sound very effectively. So it's acoustic shielding. So we'll find there'll be all sorts of different things. I suspect that looking longer term, we'll probably have people seriously considering the space elevator. People seriously using new materials in rockets, for lightweighting, radiation shielding, more recycling of water and fluids and various other things, gas separation, that sort of thing as well. The list is endless. It's really, we're looking at a materials revolution going forward, and the space industry is going to be right at the front of that because you rocket boys love playing with new materials.
Well, Adrian, it has been a fascinating conversation, and I really appreciate your time today. So thank you so much.
It's great. It's been fun. Thank you.
Adrian Nixon is Editor-in-Chief of Nixene Publishing. And that is going to do it for this edition of the Ex Terra Podcast. You can subscribe to the audio version of the podcast on Spotify, Apple Podcasts, and many other popular podcasting platforms. Be sure to click on subscribe to make sure you don't miss an episode of the podcast or any of our other videos. You can also get daily news at xterrajsc.com. And one thing more, be sure to connect with us on LinkedIn and follow us on Twitter at Ex Terra JSC. Until next time, I'm Tom Patton. Thanks for joining us.